Our speaker tonight is our own Dr. Cynthia Cheung, RTB Fellow and visiting scholar, translator into Chinese of Navigating Genesis, an astrophysicist who recently retired after 35 years working on NASA space missions. She has a PhD from the University of Maryland and an AB from the University of California, Berkeley, both in astronomy. Cynthia had a bicultural upbringing and became a Christian in Hong Kong when she was very young. She recently, as I mentioned before, completed the monumental project of translating Navigating Genesis into Chinese. Please join me in welcoming Cynthia.
I'm going to talk about how elements are created, but there are many elements in the periodic table, as you know, so I would try to concentrate on the one that matters most to us. Is the elements is important for life. I hope by the end of this talk, you'll be able to answer parts of this question. I may not be do it very much justice, but I try my best. Where do these elements come from? The elements that made up our body, do they represent the cosmic abundance? Are they universal? And how do they get to Earth? As you have heard in many programs, TV programs about astronomy, that we are made of stardust. And the Bible does say that we are made of the dust of the ground. So where did those dust came from? Just to briefly introduce you what our composition of human body is. I think Kirby can do a much better job than I do. I'm no astrobiologist. But DNA has these oxygen, carbon, hydrogen, nitrogen, phosphorus, and sulfur, which is very important. And composition by mass, actually, or you prefer by weight, we are mostly oxygen by weight, okay? In terms of our atoms, that's not the case. It's mostly hydrogen. Actually, if you talk about human being, we're mostly water, because H2O. And then we have carbon-based life, and we have fair bit of nitrogen, and there are a lot of others. The others are also very important. I'll come to that a bit later. So I try to concentrate on these, excuse me, mostly lighter elements. That how did come to make up our human body. So I first briefly run through history, how human beings view the basic structure of matter. In the very way back, 450 BC, and in China 550 BC, we all thought of all the matter just composed of 4 or 5 elements. In the Greek, Empedocles, he says it's composed of four elements: it's earth, air, fire, and water. And Aristotle supported this theory. And the Chinese always think that everything composed of 5 things only: gold, wood, water, fire, and earth. So whatever you think of, it's either gold-based, wood-based, water-based, fire-based, or earth-based. There's some truth to it if you're just observing the macroscopic properties. And along come, 50 years after Empedocles, this guy actually is very good. I guess it's Democritus. He said matter is made of tiny indestructible particles called atoms, continuously moving in space. He's getting very close to the modern view. However, because Aristotle supported Empedocles' view, everybody disregarded his view about matter being made up of small, the tiniest indestructible particles. So that view was held for a very, very long time until we come to the modern era. I fast forward to the 19th century, Dalton, among the first ones who proposed that all matter, if you divide any matter, continue divided, what is the smallest indivisible part? And he said that those particles are called atoms. It's the first time we encountered the word atoms. Okay, 2019, all of us will remember it as the year of the pandemic. However, there's something else that happened on that year. That year was actually UNESCO commemorated the 150th anniversary of Dmitry Mendeleev's publication of the periodic table of 63 elements. He published in 1869. That was the view of his original periodic table. and it's ordered by atomic weight. It's very different than the periodic table you are familiar with from chemistry class. However, he was the first one who published it in a cyclic manner and saying just from the behavior, chemical behavior properties of the elements he knew at that time, which is 63. The amazing thing is he knew nothing about atom, nothing about molecules at the time, just from chemical properties. He managed to put together this table. And in UNESCO's statement about this commemoration, they stated it's the beginning of studying of chemistry or the basic property of matters. The periodic table of chemical elements is more than just a guide or catalog of entirely known atoms in the universe. It's essentially a window on the universe, helping to expand our understanding of the world around us. So he did a very important thing, a milestone in the terms of scientific development. So I go on to show you the modern periodic table. The one that Madeleine showed was actually the vertical, which is very odd. That's why you're not used to seeing it. The one that we are using nowadays might be in the wall of some of you who are chemistry major. I heard that Frasvano is crazy about periodic table. It is arranged by atomic numbers, not by atomic weight. So it's very different because now we know the isotopes. So, and here are some more familiar category of different kind of material. I downloaded it from the American Chemical Society, so I guess it's up to date. So nobody knows when the periodic table will end. People are still trying to extend the periodic table to much higher elements. The reason we don't see these elements is because they are short-lived. They're mostly radioactive. The amazing things of Mendeleev's periodic table at that time when he published it, he left gaps to say that there are elements I have not discovered, but I know they exist. Smart fella. He know the 63 elements he published was not just those. There are more to come. So they increase our knowledge of the basic structure of matter. J.J. Thomson is just like a march of Nobel laureates from now on. He discovered electrons. But his model is not correct at that time. He used what I call the plum pudding model. He thought that the electrons are just, embedded in something, within the atoms. Okay, so the atom is not just the basic thing. There's also electrons in the atom. Along comes Rutherford. He's the father of nuclear physics. Because of his experiment, he found that there's a nucleus, and nucleus surrounded by these electrons, and these electrons are orbiting. Okay, maybe in the cloud, according to Rutherford, and then along came Niels Bohr. He actually put in quantum physics at that time, and for the first time, he came up with what we sometimes call the planetary model of the atom. That the nucleus, between the nucleus and the electrons, there's a great space there, and the electrons can only take on specific orbits around that nucleus, and they have special transition. They're quantized, so each level of those electrons take on specific energy if they were to transition from one shell to the other, and that's the modern concept used very much to this date. They marry the atomic structure with quantum physics. So we are into the 20th century, and that's where things change very, very fast. Very interesting. Those days, these guys really, they were able to travel and meet together. So their ideas actually cross-pollinated. So that ended up to be a very new idea of the atomic structure. And then come the nucleus. Once Rutherford started the nucleus, things started to moving along very fast. And these other people, Henry Becquerel, Marie and Pierre Curie, they started radioactivity. They discovered radioactivity. As many of you know, Marie Curie subsequently won the second Nobel Prize because of her work with radium and also polonium in honor of her home country, Poland. Marie Curie also started the use of radioactive material for medical application. And of course, she herself, unfortunately, she didn't know enough about radioactivity at that time. She actually died because of her close, working with all these radioactive elements. And later on, of course, simultaneously almost, Frederick Soddy and also Francis Ashton also discovered isotopes. It's the nucleus itself has also composed of not just a fixed number of nuclei, but there can be protons and neutrons. So some elements might have the identical elements, some might have different number of neutrons, and some of them may be radioactive, and they can transmutate or change from one isotope to the other with emitting a radiation or in a particle. So we are getting to the modern view of matter now. At the same time, that's where my role as an astrophysicist comes in. People in astronomy are thinking about the energy source of the sun and the stars. It's all almost simultaneously. The two-branch nuclear physics and astrophysics never touched base in those days, but people are also thinking of those problems. How does the sun shine? Where does the sun get its energy? So then many ideas at that time, the major three ideas is gravitational energy. Because it's a big ball in the sky. It's heavy. We know roughly how big it is. But computing it, this is a Kelvin homos, using thermal energy generated by gravitational energy. They computed it, they say, no, it won't last. Because by that time, geophysicists already know by the dating method, they have radioactivity, so they dated the Earth's rocks. It's around 4.5 billion years old. So the sun must have lasted longer than that. It cannot be 20 million years. Gravitational energy alone cannot sustain the sun shining for this long. So that won't work. So the other thing they know about is nuclear fission, which is an element with high atomic number with special isotope. They can give out radiation or a particle. And by that, they can sustain the sun because it gives out energy and gives out warmth. By the way, that's how the Earth maintain the interior of the Earth, maintain its dynamo, and also have the tectonic activity, because the center of the Earth full of radioactive uranium, plutonium, and all these other things keep our interior of the Earth warm. But could that work also in the sun? But they dismiss it very quickly, the astrophysicists, because they say, I don't see any of these elements in the stellar spectra. So those elements apparently didn't exist in the sun. It might exist in the interior of the Earth or on the rocks, but it does not apply to the stars. And they didn't see it in other stars either. So they say, well, that likely won't go. Maybe part of it is it, but that it could not be the major source of energy. And came along Sir Arthur Eddington. He has been thinking about this problem for a long time. Actually, he was one of the ones who said that maybe gravitational energy will work for the sun. And then all of a sudden he thought about maybe the stars. Now that we discovered nuclear fusion, can the stars be the crucibles in which the lighter elements, which are bound in nebula? By observation, they know that we only see hydrogen and helium mostly, in the universe by the spectra. Can they be compounded in more complex elements? In the stars, matter has its preliminary brewing to prepare the greater variety of elements which needed for a world of life. So the first time he thought of whatever happened in the nucleus has implications for the macro structure or the large scale structure of things in the universe. It's the first time he just actually put those two together, integrate the two together. So nuclear physics has implication for astrophysics. But at that time, his idea was not received very well. People say, nah, nuclear fusion in the sun, how can you do it? The reason is there's a problem. Nuclear fusion would mean putting two nuclei. They're both positive charge. They are protons, but neutron doesn't have a charge. We try to put two protons. They will repel one another. There's a Coulomb barrier. How could you put them together? So the only way you can put them together is Russian already thought about quantum mechanical effect. He proposed a tunneling effect. There's a finite probability, according to Coulomb, that you can transverse the Coulomb barrier because of this tunneling effect in quantum mechanics. And here are the equation and the proportion to temperature and energy. So the nuclear reaction rate is given by the integration of the Maxwell distribution, is how fast your particles are going if you have a group of particles, and the tunneling barrier. And that gives you the penetrating probability on nuclear reaction rate. And this is called the Gamow peak. That is what they call nowadays the nuclear reaction rate. At that time, people touted Arthur Eddington and say, well, that is not hot enough. The interior of the sun is not hot enough, may not have enough energy nor the temperature to do it. And Eddington usually just dismiss them and say, well, you go and find a hotter place. If the sun is not hot enough, nuclear fusion, then you go and find another place, because we now know the interior of the sun is 15 million degree Kelvin. So I say, well, if it doesn't work, then we can't make it work anywhere else. So that's how the science progressed at that time. You say, likely this will have to work. Okay, why do they think it work? Okay, they have to do some, at least back of envelope calculation before they say it will work. Because Einstein at the time already proposed the theory of general relativity. We have E equal mc squared. Excuse me. Just having mass of the sun. We know how much proton weighs. We know the hydrogen has only one proton in the nucleus. So if you combine 4 hydrogen atoms, if they would combine together to form a helium nuclei, then you emit the binding energy, and they weight, both the 4 protons compared to the weight to helium atom, because you come up with extra energy, and that's the fusion energy. So if you look at that, that's quite a bit of energy. You don't even need all the mass of the sun. You only need 0.7% of the original mass. If the nuclear reaction can just convert this little much, and we know the solar luminosity, we know how much the sun output every minute that can be measured. If you do that, the sun can shine for 10 billion years. Now that's okay, because we know the Earth was around 4.5 billion years old. So there's more than enough to sustain Earth. And we know the sun has been around for quite a while. At least it's longer than the Earth. It has to be longer than the Earth. So they say, well, at least the order of magnitude, everything works. It's nice to say that, but then how do you make it work? Okay, fast forward again. I try to bypass the history part as fast as I could. Come 1957, of course, all these ideas have been brewing, in various fields in nuclear physics and astrophysics and all that. This is ostensibly a review paper published in the Reviews of Modern Physics by Margaret Burbidge, Gordon Burbidge, William Fowler, and Fred Hoyle. This paper is called, because of the it's an acronym called B2FH paper. It's one of the most famous papers in the field of nucleosynthesis. It actually reviewed all the ideas and ongoing, but it did more than just review. It actually, in that paper, after they get everything systematically together, they also predicted some new things there. And they lay out the schemes by which different elements of the periodic table were formed. And I just blow up, what they quoted in the beginning of the paper. They say, it is the stars above us governs our condition. It's quoted from Shakespeare. King Lear, Act 4, Scene 3. He say, yes, this is the stars. And they lay out the entire scheme and also the way by which nuclear fusion can occur in stars. So the field of nuclear fusion was established, pretty much everybody agree, established by the publication of this paper, because they get all the ideas together from nuclear physics, from astrophysics, everything is together in one paper. And a lot of people refer, and I at least read through it once as a graduate student. By the way, nucleosynthesis was my field. I almost want to tell Kirby, I cannot go on this talk because, my golly, because of my move, I couldn't even locate my thesis. Maybe it's still in a box in the garage. I really could not even locate one copy of it. I have at least 10 copies around, but maybe it's still boxed up in the garage. So, but anyway, it's a must read for anybody who's in nucleosynthesis because it's laid the foundation. Okay, now here comes the modern periodic table, and the schemes are laid out by this paper and how things could be created according to by stellar and by the different mechanisms, including stellar. They started with the Big Bang. The cut is color coded. I don't know whether you can see it well on your screen. It's color coded according to the mechanism by which they produce. I will go through each mechanism, briefly at least. Hydrogen, helium, and pole of lithium are created by Big Bang nucleosynthesis. Now, most of the rest are created by stars. You can see the color coding. It's different kinds of stars. I just merge all of them together. And some of them are what they call, this is normal stellar nucleosynthesis. There's explosive nucleosynthesis, which happened at the end of the life of a star. So they include all these dying low mass stars exploding, more massive stars exploding, white dwarf, and merging neutron stars. This is an explosive event that happened, cataclysmic events. And there's a fourth mechanism that's still ongoing today, is cosmic ray spallation. I mentioned that briefly at the end. So there are four major areas, mechanisms by which elements can be created. That's too fast. Okay, so I just abstract that eye chart for you. What it meant that their scheme is that some elements are actually older than the others. Not all the elements in the periodic table are created at the same time, because the Big Bang, of course, preceded the first generation star, preceded many generation stars that will come after that. So you take a look at this and try to take an image of this so you remember this. In the upper left are the Big Bang elements. And slightly below that group of elements can only be created in the first generation star. However, you want the entire periodic table, about 100 elements. Some of them are rare, but they require multiple generations of stars in order to be formed. It cannot be formed in the first generation, nor cannot be formed in the first, maybe even a million years after the Big Bang. And also included in this schematic is that some of the elements that may not be included in the normal periodic table, they're in yellow, and because they're very short-lived radioactive elements, they're only made in scientific laboratories, and they measure in and they disappear in a very short period of time. Those are the elements which we call very short-lived elements, and highly radioactive, and the half-life is very short. Okay, you remember the past diagram, and now I show you what are the elements in the human body that are required for life. These are the, these are the parts in the DNA. CHNOPS is carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. They're scattered all over the place. They could not be made in the first generation star. They have to go through multiple generations of star. That's the message. So if you live way, way back, you would not see the elements that are required from human life. And that's why Hugh Ross in Why the Universe is the Way It Is, they say every single galaxy, every single star is important before human life shows up on Earth. Because without them, you don't even have the basic building block of life. You need all these elements. I will go further into that because even if you have BCNH, it's okay. But the other things, which like the ingredients in the back of your vitamin bottle, those are necessary for you. Or some doctors say these are vital poisons. You need some of that. You don't need a whole lot. These are trace elements, which are extremely important for health. You lack some of that, you're in trouble health-wise. So you won't live a very long life. So these are very important elements, and those could only, some of them could only be made in some very difficult situation, meaning explosive in nucleosynthesis. So you have to go through some maybe supernovae or maybe even hypernovae in order to get those elements. So that says a lot about life on Earth later on, okay? Okay, now I go through each of those mechanisms, and there's some details, but I hope you can bear with me. Big Bang nucleosynthesis. In the beginning, after maybe 1 second after Big Bang, everything is a huge ionized plasma. C equal mc squared, so there's mostly photons and matters are all mixed together, and there's no stable atom, so to speak, because everything is ionized. Finally, when they expand up to a certain stage, then things could start recombination. And the neutron can manage to get hold of a positron and change it to a proton. And that's when hydrogen was formed. There are two paths where they could form. Or the neutron can grab hold of a neutrino and form a proton, which is also hydrogen plus an electron. So there are always multiple paths to get something. And deuterium also form, with this is the gamma ray. A proton can grab a neutron and form a deuterium with emission of gamma ray. These are all, energy generating reactions. And the helium, a good part of helium is also formed during the Big Bang. The deuterium, started with the deuterium, add the proton, become helium-3, and the two helium-3 combine with a proton to form the stable isotope, the more abundant stable isotope of helium-4. Helium-3 is also a stable isotope, but form, the proportion is much less. Lithium, we do have a problem. Nobody has solved the lithium problem yet. We didn't understand the lithium abundance to date. There are a lot of issues. They don't even know exactly what nuclear path it took to be formed, but there are really primordial lithium that was formed. Otherwise, we wouldn't have some of the reaction that would come later on. And so these, according to cosmologists, are all in a good agreement, the abundance of all these with the standard hot Big Bang cosmology. Because it's very important. It actually how astrophysics really couple with the cosmology, the study of cosmology. The two actually reinforce each other. You say it spans 9 orders of magnitude of the abundance, and they're all correct. That's why they sort of confirm each other. That's the way you measure it, and that's the way we found it in the first 3 seconds. Then everything is done. After that, they say the freeze-out occur. What happened is because the expansion rate of the universe is so fast that the universe cooled down too fast for any more nucleosynthesis to take place. In the beginning, it's very, very hot shortly after the Big Bang, so everything has to take place most of it takes place within seconds, within almost 1 second. After that, everything's done. Whatever abundance you have will be the primordial abundance. And so what we look at this, especially Hugh Ross can go a lot more in this because it's more in the cosmology than I am. I'm really a novice in cosmology. I only know a little bit. It's especially sensitive to the baryon density or matter density of the universe. So that has to be fine-tuned at the very beginning. If you slightly smaller, then nothing beyond helium will be formed. If it's slightly heavier, the mass density is higher, then all the hydrogen will proceed to helium and maybe even proceed beyond helium to all the heavy elements. Then you have no hydrogen and no helium left for life. Because hydrogen helium is very important for life. Hydrogen is very important elements for life. So you cannot, you have to fine tune it, very well. And that's where God's design comes in. Why does it have to be that way? We don't know, but that's the way it is. We are the end result, and we see what's happening. And the best model in cosmology now tell us this is mostly correct. People are still doing different cosmology, fine-tuning the model, and other cosmology other than the hot Big Bang. They're looking into how to transform. But any cosmology model has to explain the abundance of these primordial elements to this kind of precision. That is 9 orders of magnitude of abundance. They all have to fit correctly. Okay, now we come to the stellar nucleosynthesis, which is the area I'm more familiar with. I just show you the end result, which all of you have taken Astronomy 101, you will know. Nuclear fusion proceeds in the core of the star. And if the star is massive enough, they proceed to burn helium and carbon, oxygen, neon, magnesium, silicon, and they ended up in iron. The reason that they end in iron, because all the other nuclear fusion will give out energy, exothermic. But iron, beyond iron, you cannot burn it without taking in energy. So that is not energy generating, mechanism. So if you try to do any iron, that will be an explosion. That's when the star will end. So this is a very interesting area. I will go more into the detail of each stage of burning. The proton chain is CNO cycle and triple alpha process, and how God's law comes into that. And most of you have heard about the anthropic principle. In fact, anthropic principle didn't start with Carter and the other fellas. Way back actually, 1957, Robert Dicke is the first one who actually initiated the idea of an anthropic principle, because when he looked at the stars and nuclear fusion and nucleosynthesis, this is what he wrote. The age of the universe now is not random, but conditioned by biological factors. Changes in the values of fundamental constants of physics would preclude the existence of man to consider the problem. Biological factors require that the age of the universe have been roughly this golden age. We are living in the golden age. If the universe were much younger, there would not have been sufficient interstellar levels of carbon to build up by nucleosynthesis. If it were much older, the golden age of main sequence stars and stable planetary systems would have already ended. So you say everything is just right. And so Carter later on took his idea and developed what we call the weak anthropic principle. And later on, strong anthropic principle, all these things comes around and said the universe is really fine-tuned for human existence. And that's his idea when he looked at stellar nucleosynthesis and the fusion and the Big Bang cosmology. Because he's a cosmologist, if you know Bob Dicke is really, he has his own model too. So we see really God has designed the universe for life from the very beginning. Okay, so talking about stellar nucleosynthesis, I just mentioned this. Some of you might have taken astronomy, and this is why we understand how stellar nucleosynthesis work. God is into recycling too. Everything is reused. After the first generation star, when it's born in a dense cloud, the high mass star die very fast. The high mass star burn at much higher rate. And after they die, they return the substance in the stellar space. And the new stars formed from the stellar space will make use of whatever element the dead star endowed to the interstellar space. So it's a cycle from beginning to end. Nothing is wasted. But the end result is that all the material gradually enriched by higher and higher elements in the periodic table. That's what happened. Okay, the other part that any nucleosynthesis has explained, most of you might have heard about the, sorry, I clicked too fast, Hertzsprung-Russell diagram, which the astrophysicist has already been created by classifying stars according to the spectral types and their temperature. O, B, A, F, G, and O. By the way, astrophysicists always do things left to right, and they could reverse everything, okay, upside down. In the middle is the main sequence star, and there's stars that are of the main population of stars. The tracks tell us how much time they spend in each region of the HR diagram, the Hertzsprung-Russell diagram. There are fewer stars in this region because we think they spend less of their life there. And the white dwarfs are down here, the red giants, supergiants. Most of the stars send their major nuclear fusion stage in the main sequence. So any nuclear fusion and nucleosynthesis theory has also explained the life cycle of stars and the evolution history. My thesis is actually doing a model of a red giant on the CNO cycle and explain whether some new changes in reaction rates and also as a boundary condition will change the evolutionary track by varying the different abundance, because nobody is quite sure from observation what they are. So any good theory has to explain not just the abundance, but also the evolutionary history of the stars. Okay, here comes the proton-proton cycle, which we think power the sun. Now, there's several paths. There's three chains. The first one is the proton-proton chain, which is the simplest one that everybody can think of. You take 4 hydrogen nuclei and build that in. It's a gradual build up to a helium nuclei. So it's one, you add that to deuterium and then add another one, and then there are two helium-3 nuclei. Each one of them will contribute took out 1 hydrogen nuclei. So ended up will be 4 helium, 4 proton in the nuclei become a helium nuclei. Just note that this chain actually consumes hydrogen as they go along. There's another way. This is a direct fusion. It's just built up from the lowest atomic number to the higher one. That's another way, because they don't know about fission. How about building something up to higher and let fission take care of the rest? This is another way. It's called the proton-proton 2 chain. It's using a helium-3 and another helium-4 nucleus and build up to beryllium-7. And the beryllium-7, being quite unstable, will decay immediately to lithium-7. And the lithium will add another proton and create 2 helium nucleus. That's another way of doing it. And that yet another way is called the PP3 chain. If you started with beryllium, a much higher, if it's around, okay. Obviously cannot go with a Big Bang. This is in a stellar nucleosynthesis where the star already have a smattering of some other elements. You started with beryllium-7, you can add a proton, and it becomes a boron, and the boron again decay and become a beryllium, and the beryllium again a very unstable nuclear, and it decay to two stable helium. So there are multiple paths. Now, how do you prove all these? You may say, if you don't know very much about nuclear physics, well, this is all hand waving. You just, it's just all like arithmetic. How do you add, two numbers arrive at 4? Okay, there are multiple ways to do it. You can add 3 plus 4 becomes 7, and minus 3 or something like that. So it's just maybe simple arithmetic. But how do you know it's true? Which one will go? So you need to have evidence to prove that this reaction actually took place in the interior of stars. Please notice that energy is not the only thing that's produced in this nuclear fusion. There are other particles. This is a neutrino, the new electron neutrino. There's a gamma ray. Here's again another neutrino. This is another neutrino. Neutrino has a very good property. Those who are particle physicists, there are quite a few physicists in our midst. Neutrino has a very small cross-section. Essentially, it can zoom through all matters, almost nonstop. That's why it's so difficult to detect neutrinos. So scientists are trying to detect, to prove that nuclear fusion actually occurs in the center of the sun. So they're trying to find a nuclear neutrino from these reactions. If we find them, that means, yes, the sun is actually undergoing nuclear fusion. Because you may say, why don't you look at gamma ray? Unfortunately, the sun is a pretty dense object. Most of the photons produced in the sun's interior, even gamma rays, it goes through multiple boomerangs before it reaches the surface. So the average photon takes 1 million years of travel from the center of the sun to the surface. So we won't see anything happening in the interior of the sun. What we'll see is the atmosphere of the sun. So we don't know actually what happened in the interior of the sun, except for these neutrinos, which is a direct proof. It takes almost no time for it to zoom out. It has been a big conundrum for a long time. That was happening in my graduate school and postgraduate school days. People were scratching their head. We couldn't find those solar neutrinos. We have very big detectors built. You're familiar with solar neutrino detection. They build a huge tank to try to, you need a lot of mass to detect the neutrino because they react so, the reaction rate is so small. They measure some, but only 34% of expected value. Say, are we wrong? Do we get all the nuclear reaction wrong? So that's another instance of where particle physics and astrophysics sort of help each other. So people were scratching their head and say, what's going on? We think for sure has to be nuclear fusion because they find another kind of energy source, but where are the neutrinos? Finally, the particle physicists figured it out because they figured there are different flavors of neutrinos that are produced. Later on, I come to the next cycle, then they understand. The neutrino actually change flavors. There's we pointed out here the electron neutrinos. There are the muon neutrinos. There's also called the tau neutrinos. They actually change flavors during propagation from the interior to the point where they leave the sun and propagate to Earth. So actually what we are measuring is correct, and it resolved the puzzle. And these two guys who built two major detectors, this is, I think, is Ron Davis, and I can't pronounce the Japanese name because Shiba is another collaboration that built the detector. They won the Nobel Prize for developing the detector for detecting neutrinos in 2002. So that problem is solved and understand exactly how the sun produced, and it's really the PP cycle. Let me go to the next chain and explain a little bit more about different kinds of neutrinos. Along came another guy, Hans Bader. He said there's another way of creating nuclear helium nucleus. Because we are no longer in the first generation star, there are already some smattering of elements like carbon, nitrogen around. We may be able to use those atoms, those nuclei, as a catalyst to help to fuse the four to become the four helium nucleus. So you say, why don't we start with the carbon-12? We add a proton, which is a hydrogen nuclei, and then you proceed like this, okay? And from the product, you become an N13 isotope, and that decay with emission of beta particle, and then also another neutrino, and with emission of energy. So every step, it takes the product of the previous step. But at the end, you don't exhaust any of this catalyst. It comes back. So depending on the energy level, they can proceed all the way, and you get back all the elements. You start out with the carbon-12 came back. It started here and came back, but with the creation of a helium nucleus with emission of energy. The total energy that's generated in the CNO1 cycle is 26.73 MeV, which is not small. Actually, this idea didn't originate with Hans Bader, but he won the Nobel Prize because he didn't just thought about idea, he actually did the computation about the reaction rate. He's a very good nuclear physicist. He actually did the entire computation, explain how much energy is expected from each one of them. And he actually really became known as the guy who actually propagated the CNO cycle. And he also has other CNO cycles ongoing. Depending on temperature of the star, they have CNO2, CNO3, and CNO4 cycles operating. And even in the explosive nucleosynthesis, the hydrogen fusion still continue. The last time I showed you the onion structure of a star, after the hydrogen is exhausted in the core, the hydrogen continues to burn in the shell, although it stopped burning in the core. Helium burning started in the core, but hydrogen continue in the shell, but in the outer shell. So in explosive nucleosynthesis, it's again hydrogen dumped onto a highly evolved star, and again it starts a runaway of CNO cycle. And it's very, very fast CNO cycle, and that becomes CNO3 or CNO4. But they use other nuclei as a starter catalyst. Now talking about neutrinos, okay, they was verified. The direct verification of the CNO cycle was this. This is Italian collaboration. They built again another detector, and they detected the specific. By the way, the neutrino has a spectrum of energy, so the different energy level. So you build a detector, you detect a different kind of neutrino from a different energy range. And so it's a Borexino collaboration. And they actually, in 2020, they published a paper. It's a direct evidence experiment. They actually detected exactly as Hans Bader predicted the energy of a neutrino emitted by the CNO cycle. So you may ask, well, what is actually operating in the sun? Actually, the sun is in a very peculiar place. As I said before, the sun was around 15 million degrees Kelvin. Now, the two chains are different temperature dependence. The CNO cycle is highly temperature dependent, T to the 17th power. PP chain is only T to the 4th power. And there's a crossover point about 18 million. The sun is kind of on the edge. So the sun does have some CNO cycle operating. That's why they managed to detect some neutrinos produced by CNO cycle from the sun, and they also detected some of the neutrinos from PP chain from the sun. So actually both are operating, and in certain part of time of the life of the star, sometimes they cross over depending on what temperature you are at. So it depends on which line you are, where is your energy rate, and what is your temperature. And so it determines which one is dominating. Sometimes they are equal, sometimes one is less, one's the other. Okay, now I'll give you another eye chart. This is nuclear physics. I'm glad I'm not a nuclear physicist, otherwise I need much better glasses. Here's the energy level. They are also quantized, just like the electron, in the chemistry. So some of these are theoretical, and some of them are measured. They try to say, different states, the excited state, the ground state of each nucleus. So how do you measure the reaction rate? Because all these computations depend very much on the reaction rate. So I say the Gamow peak. How do you compute that? You have to understand, for example, C12, where it's excited, where is the ground state, so what energy level it is at. So, but those energy level, there's also, there's a wave function. There's also, a Maxwellian distribution. They say even if at the wings of the resonance, it will go faster than if you were completely outside of it. So the one way to find the highest reaction rate is look for resonances in the stellar energy range. And this example is actually goes to the helium burning. First, they don't think the helium burning will go at all. And some guy started to say, well, look for me for this resonance. I think it's around this area. Go look for it. And guess who that guy is? Now, this is the measurement technique. I just inserted two old pictures. These are two labs that did a lot of work. By the way, the accelerators. I think Kirk Rashid can tell us a lot about Berkeley and synchrotron. This is an old picture. The color radiation lab is the lab that in Caltech that did the most in measuring nuclear reaction rate in the stellar energy range. And these are the equipment. They're all accelerators, one solid the other. They bombard a target, trying to reproduce the fusion reaction in the star and see, the yield and see how fast they go, and so deduce the reaction rate. Sorry, I jumped too fast again. So the helium burning. This guy was called Fred Hoyle. A lot of people say, well, helium burning, you're trying to mesh together 3 helium nuclei to form a carbon 12. Of course, helium has 4 protons. Now it's even harder than pushing together 4 protons of each nucleus. You're pushing together 4 by 4 by 4 to get the C12. It's very difficult. So, and also, if you push together 2 first, you produce beryllium-8, which is highly unstable. And it actually decays in a split second, 8.19 times 10 to the 17th seconds. Unless, during that time, a third particle fuses with beryllium-8, produce an excited resonance state of carbon-12. And that is called the Hoyle state. He actually predicted that one. And this guy, that's why some people call him the father of nucleosynthesis. He was a co-author of the B2FH paper. He actually badgered in William Fowler in the Kellogg radiation and say, hey, please go and look for this resonance. Remember that eye chart? He said, go look for the resonance around this energy range because there's so much data, you don't know where to look. Go and look for it. And they found it. So this reaction is firm. They actually have experimental verification of the actual nuclear reaction rate. And so that state, so somehow, because he said, well, it has to go because we have helium we know the end result, we have helium in the universe. So this reaction has to go because I have found no other way. So upon looking at all this, of course, most of you know Fred Hoyle is not a Christian. He's, I think he has Hindu influence and he won't acknowledge. He said this, and this is a quote from an article he wrote in Engineering and Science in Caltech, which is a magazine issued by Caltech. And most of you have seen this quote one way or the other, but you might not know the context when he said that. A common sense interpretation of the facts suggested a super intellect has monkeyed with the physics as well as with chemistry and biology, and that there are no blind forces worth speaking about in nature. The numbers one computes from the facts, calculates from the facts, seem to me so overwhelming as to put this conclusion beyond question. He was wowed by the energy level that's so fine-tuned. If beryllium-8 plus helium-4 does not end up so close to the resonance stage of carbon-12, the reaction won't go. And also for two helium atoms to come together to become a beryllium-8, which can decay in such a split second, but within that short period of time. In fact, most of the time it won't go, but it's 1 in like 435, the probability. One will take, and just in that period, and this reaction will go forward. And so he himself was very impressed, and he made this statement. Now it's recorded in an article. So we say, well, God's hand is designed the law so that the elements could be built up. Okay, I just keep going. Don't know how am I doing in time. Okay, that's another way to verify whether nucleosynthesis actually is taking place in stars. Because astronomy, we seldom work in the lab. I can't touch anything. Everything is remote. The way we can touch, as Psalm 19 said, the universe sends out a message every day, and that message is by light. So spectroscopy is what we work with all the time. We look at spectra of stars. How do we know that the stars are actually creating these higher level elements? Because most of the elements are trapped in the interior. They seldom come to the surface. However, then the number of stars with the convective zone. So some of the things created in the interior star through convection occasionally came up to the envelope, especially in the evolved star in the red giants. So in 1952, it's very early on in the history of nucleosynthesis, because 1957 was the B2FH paper was published. They found technetium. Technetium is not a natural occurring element on Earth, because technetium half-life is around 1 million years, if I remember correctly. 1 million only, okay? And Earth is 4.5 billion. So whatever was there is already gone. It's already completely decayed. They found it in stars. So it must have been created recently. So something is ongoing. My thesis, I couldn't give you a reference now, but there other people have written papers about this. CNO, because we continue building helium into carbon and nitrogen and oxygen, the isotopic ratio should be changing in the highly evolved stars, especially in the red giant stars. And yes, they do observe the change. And later on, I will talk about the explosive nucleosynthesis. We do observe, and there are multiple observations, supernova, ejector, and remnants that show radioactive elements. And they decay very fast, so they have to be created fresh or very near term, very recently. They have not been around forever. So spectroscopy is something we rely on greatly to do the verification. Okay, now here comes the explosive nucleosynthesis. I go through this very quickly because I think I don't want to bore you with too much details. This is another diagram showing you how stars evolve. There are 3 kinds of stars. They usually be divided in computing stellar evolution, high mass stars, low mass stars, and really they won't even qualify that a star called the brown dwarf because they hardly shine. That's why we call them brown. They go to different evolutionary path. And Earth, like the sun, I mean, a star like the sun will go through a red giant stage. When it exhausts its hydrogen, the envelope will expand. The core will collapse, and that's the end of Earth. By the way, the envelope will expand beyond, I think, almost to the orbit of Jupiter. And then the envelope will blow off. And what is left will become a white dwarf. That is, when it blow off, you become a pretty planetary nebula. And that may be the ultimate fate of our sun. And of course, the outer envelope is blown off. And so that got recycled into the interstellar medium. But if you become a white dwarf and you have a companion, if you were not a single star, now the sun is very exceptional in the sense that it's not in a binary. Most of stars in the universe are in binary or triple star systems. Our Earth is very unique in maybe we have lost our twin. Some people have speculated maybe Earth on time had a twin, but we lost it. But if we were in a binary system, the white dwarf will circulate the red giant and suck the outer envelope into the white dwarf envelope. And that might, when they accumulate enough, it becomes an explosive event because it's very hot on the surface white dwarf and become what we call type 1 supernova. Type 1A supernova is very important in the sense that because they all started from white dwarf, which has a fixed envelope. Some of you might have heard about the white dwarf Chandrasekhar limit. It's 1.4 solar mass. It's almost the same. So it becomes a standard candle measuring the distance to the universe. They all have roughly the same luminosity. So we use it as a standard candle to measure the distance. Or it become a nova, sometimes become a recurrent nova, that it blows off at periodic fashion. And there's some white dwarf that has no companion and gradually die off, become a black dwarf. Now, for the very massive star, that's where the interesting things happen. That's where the supernova happened. It continued to burn like the onion skin diagram I show, continue to burn to higher and higher fusion to elements until iron eventually called collapse. And it become a type 2 supernova. The Crab Nebula and other very spectacular supernova fall into that category. And depending on the scale of the explosion, it could become a neutron star or a black hole. There may be no remnants left. And it became a neutron star, it became a pulsar. The pulsar is one of the most accurate clock in the universe. It generates, most of the pulsar has very high magnetic field, and it may be the source of all the cosmic rays. The black hole, although we call it black, but it has an accretion disk, just suck a lot of material around it. What we see, if you say you image a black hole, what you image is an accretion disk. It gives out a lot of X-ray and sometimes gamma ray radiation. So these are explosive nucleosynthesis events. And in those events, that's when a copious amount of neutrons are generated, necessary to build up the higher elements. Because when you try to continue to build up, you need neutrons, influx of neutrons very fast. And the S stands for slow process, R stands for rapid process. So two ways to capture the neutron, depending on the force of the explosion. So nowadays they say maybe even a supernova is not enough to do it. You need a hypernova, which is like several order of magnitude higher than the supernova to get the rapid process going in order to build the highest elements. So these are explosive. All these processes just vary, according to all the formula I gave you. They just capture usually they capture alpha particles, just keep building alpha particles equivalent to a nucleus of a helium. So every time you take a nucleus and keep adding to it, and it has to be very rapid with sufficient neutron. Okay, I just need to give you a solid example what happened. How do you prove all these processes? There's a supernova in 1987A because during my career, there's some even more spectacular ones that has gone off since I retired, but this one was during while I was still working. Supernova 87A, which caused a lot of excitement at that time because it's so close by. It's in the Large Magellanic Clouds, in a galaxy very close to our galaxy. And so you can measure it with a lot of precision. And the good thing is caught it very fast within a few days. And they went back to the data and they even caught the neutrino pulse when the star collapsed. And they were able to, at that time, luckily, all the observed, what I call multispectral observatories were running in space, including Hubble Space. This is I think this is from European Southern Observatory. There are quite a few. If you want to Google, go to Hubble Space Telescope, you got the prettiest picture of supernova 9087A online. They captured the entire light curve. Usually when you observe a supernova, usually it's on this down end. You never got this peak because you were so late. You only know, oh, there's a supernova. By the time you get here, it's already here. It's already decayed to this point. But in this case, we actually caught the peak. Multiple observatories, all the spacecrafts were observing at the same time because we got the telegram out, everybody's looking at it. And because of this light curve, they were able to prove this matches exactly the decay of nickel 56 in cobalt 56. Because of this, otherwise the light curve would decay very fast. It's just like a flash, it's gone. But because it's radioactive element, it was able to sustain it for at least 6 days invisible. And after it continued for almost 77 days. And they can continue, of course, not with naked eye, but people can see it until cobalt 56 decayed to iron 56, the stable, the finally stable nucleus. So it's very excited, but if you look in detail in this picture, they're still following the supernova, by the way, because the Random does some very interesting things. It has a shock wave going out. You can see this double ring, but this because of projection in the sky, it actually shoot up in both ends. It's a projection of double ring. There's a beam, and they ram into the interstellar medium, so causing a ring effect, and they're actually encountering material in the interstellar medium. So it's very interesting. There's the interior ring and there's the outer ring. So it's a very interesting supernova. And that actually, observing supernova actually tell us all the higher elements are being created in all these explosive events. And because when they explode, they endow all the heavy elements in the stellar medium, which has got mixed in, and then eventually form new stars. Okay. Now, the last one, it may not be very interesting, but not very spectacular. It's very slow. It's cosmic ray spallation. But this only apply to very light elements, lithium, beryllium, and boron. But these are very important elements, especially isotope helium-3. Helium-3 is important because now we are trying to do nuclear fusion as energy generation on Earth. And helium-3 is one of the stable isotopes of helium, although with much less proportion compared to lithium-4. The good thing about nuclear fusion is that you don't have radioactive, what do you call it, problem of the leftover stuff that you need to deal with, unlike uranium, plutonium reactors. What you come up with maybe water and just helium, so you don't worry about it. That's one reason, perhaps, people want to go back to the moon, to harvest this helium-3 on the surface of the moon. Solar wind is actually cosmic ray high energy particles. They ram against the various elements on the soil, and they keep producing, mostly hydrogen producing helium-3. And they estimated about 1.4 to 15 parts per billion in the sunlit area of the moon surface, just a regolith, or 50 parts per billion in permanent shadow regions. That's why they say there's a moon race now, not so much for national pride, not so much to put human there, but they want the resources. Helium-3, if you get it, you might solve the energy crisis. At least you can have the fuel for a fusion reactor here on Earth. For comparison, Earth only has 7.2 part per trillion, so it's much, much lower. So we can just go and get the helium-3. That will solve a lot of problems because they're also lithium, beryllium, all these lithium. You know how important they are for your battery. So this is, although it's a very slow going process, it takes a while, but they accumulate throughout time. Okay, here ends my talk about creation. Now the time about distribution. Where do we get all those elements on Earth to create life? We are in a very particular area in the universe. Most of you have seen this diagram before. We are located slightly outside co-rotation point of our Milky Way galaxy. But when you compare our Earth's abundance to our local neighborhood, we are the oddball, actually. Some people say, well, the sun is a normal star. No, if you compare it with its neighbors, it's kind of odd. It doesn't have the average of the solar neighborhood. It was born somewhere else and they migrated here. Because how do we come to this conclusion? Because the elements here, from supernova and hypernova, those are elements that are on Earth. At least we know it's on Earth. We have to grab them somehow. It's not incorporated into our system. But we can bear to live close to them. Otherwise, you're in trouble. The radiation from, because people say, why don't you go to the galactic center? There's a black hole. There's all these. By the way, there are a lot more supernovae close to the galactic center. You don't want to live there. You will be zapped by radiation in no time. Life won't exist there. So the sun has to be created. Some people still think, okay, there's a lot of hypotheses ongoing. One of my colleagues say that maybe the supernova that created the Geminga pulsar might be the trigger for formation of the solar system, and that actually pushed this interstellar medium to condense and form the solar system, also endow the solar system with all the required elements. There are a lot of other hypotheses ongoing, but somehow, somewhere, we have to get those very high, what I call the vital poisons, which can only be created in supernovae and hypernovae. We have to get close to those guys and grab those elements in order to sustain life. But then once you grab them, you better leave as fast as you could. Actually, we have witnessed oxygen explosion themselves might give the sun a kick, and you might leave that area entirely. There are stars we know they have run away from a cluster because something exploded and they got kicked out. I don't know how God arranged that, but somehow we ended up in this nice neighborhood. We are not in the co-rotation point, in which case we will traverse many spiral arms. It's not just bumpy. We get into very difficult situation once you traverse the spiral arm because it's area of high star formation. Again, you run into radiation, run into all this explosive events, and also high density, and you might get into cold molecular cloud, in which case you freeze. So location. You want to build your house in the places nice and quiet, and we are there. Okay, I again advanced too fast. So we also need to compare. Is Earth very common in our solar system? Because we know the Earth's abundance quite well. We have rocks we can touch, we can analyze. On the right is abundance according to Z, okay? And on the left are the solar abundance, because we can observe the sun in the spectrum very well. And you don't have to look at the details, but you can see the jacks are completely different. So Earth is kind of depleted of the volatiles. And Earth has very high, I never know how to pronounce it, siderophile elements, which is very important. These are the guys for high tech. Because the volatile elements, you could kind of explain, because we know the moon forming impact might have completely devoided Earth of all its original volatiles. Whatever we have in the atmosphere will outgas later on. So we understand why we depleted in compared to the solar abundance in hydrogen and helium. We still have some. We don't have, we still have sufficient. But these are really enhanced carbon, oxygen, silicon, all the rock forming elements. But these are other elements. How do they come? Where do they come from? Because the Earth has tectonic activity, but that's not sufficient to account for these. These are the rare earths, the precious metals, all these things. So where do they come from? And some of them are very important for human life. Some of these are what the vital poisons. So how do we get them? So the theory has been maybe, because originally the solar abundance, they're left over from the primordial solar nebula, which formed our planets, because we are in the interior of the solar system. And somehow they preferentially, the terrestrial planet, Mars, Earth, and Venus, and Mercury, we somehow acquire these things by acquiring the meteorites. They all came inside because of the sun's gravity, and so they all bombarded the Earth, and so we acquire them throughout. That's just a theory. We don't know. It's one possibility. So this is a diagram. How do we get all these elements? It's from Big Bang all the way to here. How do we get them? Primordial gas cloud, we form solar system, where the outer solar system has two asteroid belts. One is called the Kuiper belt, one is called the Oort cloud. All these guys, once in a while, get a disturbance from passing stars or some gravitational perturbance. They came through. And the comets and the asteroids throughout Earth's history may have give sufficient amount of water to cover the Earth with an ocean, and also may have sufficient life ingredients to replenish all the things that we think we need. That's just, there's a lot of back of envelope calculation. We're not sure. This is still a hypothesis, a theory of some people. So sometimes the asteroid does not do nice things. They can cause a mass extinction event, but sometimes gradually, every day, tons of material, the small particles, still impinge on the upper atmosphere of the Earth. And high-flying airplanes do catch those. And the space scientists do catch those and analyze them for the primordial abundance of the solar system. So they know we do acquire some of these things daily. And so that may be how we acquire those life-forming elements. Okay, this is the end of my talk. So I think I'm open to questions. I'll do it as fast as I could. But there are things I completely gloss over.
So my head's spinning. I'm sorry. That's wonderful. Would anybody like to ask Cynthia any questions?
I've got a question.
Go ahead, Lothar.
Yeah, you were talking about the helium-3 on the moon. How does it remain there? Is it buried underneath? I can't imagine it being on the surface.
I'm sorry, can you repeat the first part? I couldn't catch it.
Regarding helium-3, where is it really located on the moon? I can't imagine it being on the surface. It must be somehow buried underneath or something.
The helium-3 on the moon is embedded in what they call the regolith, or a layer of very rough, they call it lunar dust, but it's not dust. It's very nasty material. It's like sharp sand. Before the astronauts landed on the moon, they worry because are we going to sink into quicksand or sink in whatever? When they step on, of course, there are a lot of they call it a regolith in general. They call it has been lunar soil gardened by cosmic rays. So they have been bombarded by cosmic rays throughout the billions of years. And they're very rough stuff. The first thing they say the astronaut did at the end, when they came back, they didn't know what to pick. They just scooped out like 100 pounds of those regolith. in their bag and came back with it. And some of them are still under, sealed in the environment. And those are still waiting to be analyzed. And from that, they found out there's quite a bit of helium-3. They're all on the surface, nothing deeper.
Well, wouldn't it also be partially because the gravitational force of the moon is so much smaller than the Earth? I mean, we think of it, if it were on Earth, it would just it would well, I mean, it would be blown away on Earth because, isn't it?
Yeah, correct. Because the moon has no atmosphere, no wind, no water, no tectonic activities. On Earth, you have something like that. Tectonic activities might just recycle it, and they got buried underneath the topsoil. But there's nothing. Everything is. That's why one reason we went to the moon, the pure scientific reason, not to talk about the resources, it is a archive of the original solar system composition. Nothing has been touched. On Earth, there's the wind, the water, so there's nothing remained from the original. Everything was recreated multiple times. It's buried under I don't know how many layers of things. So we couldn't find I don't know, Ken Wolkomov was not here today. You can ask him. We couldn't find the original continental crust. We don't know where it is. There's nothing that was old, really old on Earth. You can't find things beyond like 2 billion, I think. I think north of Canada, there's a little bit of continental shield, and Australia, there's a little bit left. That's all there is of the original rock surface. But on the moon, everything was there. So we went to the moon to get the original solar system history. Everything was there, untouched.
Well,
so
thank you
the
very much.
Armstrong footprint was still there. It was not covered up.
Did you have a follow-up question, Lothar?
No, I just wanted to say I really appreciated this presentation.
Yeah, it's wonderful.
Yeah.
Anyone else? Anyone else have a question?
This is John Yu. I have a follow-up question to that first one in your comment, Cynthia. But the moon currently was born out of a collision of another large meteorite with Earth. So much of the composition of the moon, I thought, was composed of the result of that collision, and a lot of it came from Earth as well. So your comment about that the moon born the original landscape of the solar system, how does that agree with what you just said? Because it is a mixture of Earth and the original asteroid.
Yeah, at least the theory goes that the moon was formed out of the original Earth, the surface layers. That was what formed of the object that collided with Earth. They call it Theus. Likely the core was buried deep in Earth, and the other source of all these special metals and elements might be an endowment from that collider. But then the moon actually get the outer surface of the original Earth. They recondense after this fiery explosion. So they say that's why in a certain sense, moon was a lot like Earth in the surface, the original Earth, because bear in mind, the moon forming impact was only 50 million years after the Earth was formed. So it's a very short period. So it's as early as possible. And the whole condensation takes about 100 years. So whatever that is not really 4.5, but like 4.4 billion years ago. At least we got that part of history. But not anything.
I see.
Because it happened so fast. It's not after like 2 billion. It's after 50 million, within 50 million year time frame that collider, the collision happened and the moon was formed.
I see.
So it's very early. And the condensation.
Yes, if I may play back my understanding. So the moon robbed Earth of its and inherited the Earth's original surface, so much of the original surface. So what was left behind is not on Earth, not the original Earth surface, but perhaps something much deeper underneath.
Yeah. So that
That's
collision
interesting.
altered a lot. That's why they say this collision. You can read Hugh Ross' Improbable Planet. That collision did a lot of wonderful things. That collider, that impactor, actually gave Earth more iron. That set up a magnetic field. Possibly gave us all the additional elements. Of course, this is all hypothesis about what the collider composition is. Nobody knows. Okay. But that changed Earth completely. But the moon somehow got our original surface layer and we condensed. There are many simulations that went into that. Essentially, the two globs, they got pulled off one big chunk from the surface of the Earth, and that condensed into the moon. Because there's so little gravity, so it doesn't have an iron core, it doesn't have very much. We measured magnetic field on the moon, there's no magnetic field because there's no iron core. So they didn't get any of the interior of the Earth, just the surface. It's such so small body, but big enough to affect the tides, and all these other things, give us seasons, stabilize the Earth orbit, stabilize our axis, so we have seasons. All these things. The moon forming impact is a miracle. Otherwise, we won't be here. That's why when we look for exoplanet with life, we say we have to look for a system with a moon, not just a planet with water. That's not sufficient. We have planets with water, but no moon. You might not have that because that thing we're wobbling around without moons to stabilize in orbit. You won't live there.
Thank you.
The moon is important for our existence. That's why I had that presentation. You have heard it before. Thank God for the moon.
Anyone else? Terry, did you have one?
Yeah, I'm just so fascinated by the boomeranging of the photon inside the sun as it's trying to after it's generated, and then it taking an average of say 1 million years or so to reach the surface, and it's dissipating energy during those collisions. And where are the lower energy, the infrared and visible and ultraviolet, are they generated in that process of boomeranging?
When they first generate the photons are all very high energy because the interior is sun of 50 million degrees Kelvin. So the gamma ray, actually what the normal time to use is opacity, it really cannot get through because it was face a lot of roadblock. What they encounter is a lot of material between the core of the sun and the surface. So what I say boomerang actually is multiple absorption and re-emission. So likely when you get to the photosphere of the sun, when the water came out, most have become visible photons. That's what you see. The sun shines at our visible strength, like 400 angstrom to 700 angstrom, roughly, our eyes can see. That's the range. So without special eyes, like special telescope, ultraviolet, infrared, we couldn't see it. They're not, the ultraviolet from the sun is all from its the coronal sphere and the atmosphere of the sun, not the interior. When it came out, when it exit the surface, become mostly visible photons. It has come down way, because it got absorbed and reabsorbed, absorbed and reabsorbed.
Thank you.
I had a question.
Go ahead.
How have what has been the response of your scientific peers, your fellow astronomers and so on, to the idea of there being a designer or an intelligence behind all these things?
A lot of surprise. I tell people that there's a Bible studies group in NASA itself. We meet every week. Actually, most of the astronauts, to my knowledge, have some kind of faith, although of course by and large Christian faith. A lot of the scientists are Jewish, so as I say, I deal mostly with Jewish people in my in my workplace, and there are very few. I would say there are many agnostics, very few atheists that I have encountered at work. Because when you look at the universe, it's very difficult to say that to have a response. No, that's just random. I think there's a difference between physical scientists and biology. I cannot say that these things just come about by themselves, by natural processes. There's no way. Like Fred Hoyle, today he passed away. He didn't think much of Christianity. He got a very strong Hindu influence. People said that, of the people who got the Nobel Prize, he didn't. A lot of people think that he should be got because he's actually the father of nucleosynthesis. There's that rumor that Nobel Committee didn't look very, very good on his rejection of the Big Bang because he denied there's a beginning of the universe when there's abundant evidence from the microwave background. To the date, he insists on the steady state theory. That's why the Nobel Prize is saying it's not just for your work, but also for your entire career, your view of science. That's why the rumor has it. That's why he never got Nobel Prize. He rejected that's a beginning. He continued to insist on the steady state, and he even said that hydrogen is invented automatically. I don't know how he came up with that in order to sustain his theory. So some very crazy idea. Yeah.
Doug, do you had a question?
I think Doug raised his hand. Doug.
Yeah, I do. Thank you. Trying to be polite. I have two questions actually. I'm not really sure which one to ask, so I'll ask them both, and you can take either one or neither if you want. They're not exactly nuclear synthesis, but they're astrophysical questions. I have gotten this question quite often actually, and this is from people that know I have a science background, but I'm not sure if I'm answering it properly. This past summer, the James Webb Telescope published some data that was indicating that some galaxies were showing up only 200 million years after the Big Bang. And some people were touting that as evidence that the Big Bang isn't true. I don't fully understand the debate there. So I was hoping you might be able to clarify that debate and explain why that is not really a challenge to the Big Bang. That's my first question. The second question is having to do with planet formation. I've heard this a lot in young Earth creationist groups, that they claim that planets can't form because the early stages where the gases are condensing, there's enough gravitational instability. Again, I'm not sure if I got the argument correct, such that the early stages really don't make physical sense. So those are my two questions, and I'll turn the floor back to you.
I don't think I can answer the first question because I have not followed up on the James Webb Telescope result, but just on what you told me. I don't think it has anything to do with Big Bang. It has to do with galaxy formation mechanism. The Big Bang happened, then when galaxies are formed has to do with the density fluctuation and how intense they are. So one does not follow from the other. I don't see the connection. Now the second one, I don't know how the younger people were talking, what do you mean by gravitational? I really didn't understand why they are saying that. That's all I can say. Because gravity is always there, but you need a trigger mechanism for the condensation. That's why I say likely, my colleagues say that likely it has to be triggered by some explosive event very close by to push the interstellar medium is always full of matter, somewhat denser than the other. But even the dense one sometimes by itself, left alone, would not condense. You need a trigger, a perturbation. Where does that perturbation comes from? And if you want a natural explanation, it may be something exploding next to it. There's a blast wave, push it, then a lot of things could happen. And so a lot of people just conjecture that either hypernova or supernova happened, and it actually fits the bill. It does not only give you the high order elements, it also can function as a blast wave that push the solar system away from the star cluster. That's how they work. Okay.
Thank you.
Hofi, your turn.
Okay, yes. So Cynthia, this is a simple question. How is the composition of other heavenly bodies? How is that determined? You showed one slide that had very detailed composition of these elements, and I'm assuming that the ratios. How is that normally measured when you can't actually, go to that planet and sample it? I mean, is this done with just emission spectra? How is that normally done?
What we do is actually we have to thank a lot of people, very hardworking people in the standards laboratory. We do have Earth standards. We have things that we can touch here on Earth. So we have all the atoms on Earth. So we have what we call the standards spectra.
Yes.
And that every few years they updated the spectra. I think the National Institute of Standards and Technology, they do that, or they gather things from the academia and they publish that standard spectra thing. Yes. So we know, hydrogen has certain spectra, the Balmer line series, blah, 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 blah. And actually most of the stars, when you take the spectra, you match it against the standard spectra. That's how you match it to find what elements, because the stars move too. So you have to take into account the redshift, the proper motion. Yes. And you try to match that. And there's some unknown elements. Sometimes you find some unknown elements. And sometimes you say, hey, maybe that's an error in measurement, or sometimes the stars may be moving faster, and sometimes it might be a blended line from some other element. And usually it's molecular lines that we don't know about. So there are a lot of and if and buts, okay? But most of the things are pretty clear. The normal elements is very clear. It's only in some strange regions, like in the molecular region, where it's the infrared region. A lot of people are still studying it, and the laboratory people are working very hard about molarized blending is terrible. You got this broad thing. You don't call it a line, but it's just this hum there. But it actually is a composition of number of lines, and you have to go very high resolution in order to separate them in individual lines and say, oh, this carbon monoxide. And plus, it's a different region. We are used to looking at things at visible region, and we're used to be at the optical telescope. But when you go to the ultraviolet, go to the infrared, that's a mess, because a new region that we are not used to, but people are working very hard. Molecular level, they use vibration instead of emission and absorption. So it's a completely different field. So I have colleagues down one floor below just do the atomics. The atomic physicists in NASA, they do just that. Okay, measure things in the lab, and they give us a standard of measuring things and comparing. So that's how I answer you. We don't know. Some of the things we come up with a big question mark and puzzle, and we go back to the lab and say, hey, what could this be?
Okay, so the comparison with the standards, does it allow a determination of the relative amounts? I mean, I suppose it can tell you what elements are in that planet or star, right? But the relative amounts, like it's 3% of this and 5% of that, and is that possible to determine?
Yes, it's possible. That's all. My first class in astrophysics is called the radiative transfer. There's very detailed physics behind the theory of radiative transfer and how the light profile was formed. So you get to have enough high resolution instead of just having a line. To look at the line profile with wings. Yes. That actually velocity and even the rotation, everything there. So you go back to the computer and actually simulate. Sometimes there's a straightforward match, but you may say there may be some effect that cause that line to deviate from what you think it is. So spectroscopy is an entire science in itself. So I welcome you to dig into it. It's very interesting science. I'm not a lab person and I'm not an observation person, but people do that for a living. The guy who's at the telescope doing infrared, they actually run a bank of computers. We don't have money to buy a huge supercomputer, so he string together all the power max to build his own little supercomputer to analyze infrared spectral lines he obtained, because it's very difficult simulation to find the profile to match that. And by God, he found it. And that's why the lead scientist announced we found methane on Mars. The methane is very difficult to detect from spectroscopy. They never went to Mars, but they detected methane, also localized. And that's from the spectral profile. And it has also from geography of Mars and everything else. Also, there's the opacity in the Earth atmosphere, in Mars, and everything has to take into account to understand why you get a particular profile. In fact, all the atmospheric science, everybody has to take that course in radiative transfer. And most of the people scratching their head, and the professor flung half the class. The people who know what's going on, who do not know anything at all, because it's such a different area compared to the normal physics. Has to do with radiation and how light passes through a media. So it's a very interesting area in spectroscopy.
Okay.
That's a very good question and open up an entirely different field. I'm not qualified to answer that. Some people may be able to answer that much better. Yeah.
Anybody else have a question they want to ask?
Okay, I'm going to ask a question.
Go ahead,
here.
Belinda. Yeah.
Yeah, this is Belinda. Hey, so if you had like a 1 to 2 sentence and you wanted to put the stone in someone's shoe, say like a medical person, and tie it into these ideas about the elements, and your God, point about the location, just something to like have them think about. What would you say to that person?
It will take me a while to think about that. Maybe I should refer you to another person who's really a medical doctor.
Well, I am a medical doctor, but I was just wondering, like, if I had a skeptic or I just had somebody that, studies the body and stuff, and I just wanted to show them how it's very interesting that our, those specific elements are there, and then tie it into like the universe.
So
Yeah.
I can't help but interject something here, and maybe this is too far off the wall, but the triple alpha process just blows my mind, and it blew Fred Hoyle's mind so much that he even had to say that there had to be a super intellect causing it. Is the triple alpha process really the primary way we got our carbon?
Yes.
Okay, so wow, we're here because of the triple alpha process, everybody.
Yeah, there was another quote that I
I guess I would just say, what is the triple alpha?
What is the triple alpha process, Kirby?
process? I would say that.
Well, triple alpha process is where, well, I'm sorry, Cynthia, do you want to try again with this triple alpha process?
The alpha particle is actually a helium nuclei. Okay, so it's just, they call it the alpha particle. Actually, it's a helium nucleus. So that's pretty clear. Okay, they call it different thing. Like sometimes you heard of a beta decay. The beta actually emitting an electron. They call the beta particle. Okay, the alpha particle is the helium nucleus. They're just say different names for the same thing. Okay.
So basically, an alpha particle had to hit a helium atom, and then it had to hit another helium atom, and that created beryllium, which only lasts for a very short fraction of a second, and a third alpha particle had to hit that beryllium to make carbon.
Okay.
Super.
Yeah,
I don't know. I don't think my physician friend would be like excited about that.
Well, that's how
I think they would be more excited about this elements in the human body, and that they're wow. Where did those come from? And how do you tie those?
It's not from this talk, but I like Jim. What's that guy's in Texas name? University of Texas. Jim Tour.
Jim Tour?
Tour.
Oh yeah.
That it's not just getting the elements on Earth, but how do you get them all together? to form whatever prebiotic molecule you want. It's everything has to be together at the same time, same place, same. I mean, it's not, there's another step to go once you get them on Earth. How do you put them all together? Because in the lab, it's easy. Because you, an intelligent person, have put everything in a test tube. So that I form the whatever, okay. The high school student say H2O, I know how to do that. But I need a smart high school student to put H2O in the test tube. But how do you create that? If I give you hydrogen and oxygen, just splash it on, it won't happen. There needs to be an intelligent agent to interfere, to put them all together at the same place, same time. It's that simultaneity, which is very difficult to get. I haven't come to that point when you create life. That's why they say, Hugh Ross and first runner say the intervention of the lab hand is equivalent to God. You doctors, okay? I tell you, why don't you just use AI? You don't have to come to see me from now on, okay? I have all the knowledge, but then the doctor has intelligence and have all your knowledge. There's something go beyond just a database search and say, hey, you got this. You need to take care of it. But that is beyond just getting all the data in one place. You still have to merge them. That's how data become information. Information become knowledge. And when the wisdom is applying the information to the right situation, and you don't have all those together, I'm sorry, you don't have anything. You don't have life. And I love James too, how he talked tough, but then because it's New York Jewish.
Oh, as I was listening to you, Cynthia, what just now I'm kind of looking at your diagram about the sun and location. That actually describes what you're saying. This Earth had to be in the right place at the right time, put in the right place, or else those those elements would not be available for our human body. Those trace elements, that's what I kind of understood too from your talk. Is that correct?
That's correct. And actually, Hugh Ross has a good talk. Maybe he even speak better than I do about how you get the vital poisons. It's a very tough act. You have to grab the vital poison from these explosive areas. Like you have to go to a place where bombs just explode and you grab the stuff, but then you leave as soon as possible before it gets to you. And then you hurry off to this place where you start integrating everything. It's beyond me, okay, how we happen to be, everything happened to be right.
Yeah.
That's why the anthropic principle is, and it boggles a lot of people most of the people who start the anthropic principle are not Christians, but they just look at the physical laws and say, hey, how come it's just right? And it's beyond our comprehension. How come it has to be like that? So Freeman Dyson, you say the universe knows that we are coming. The whole thing that actually Carter, when he gave his first paper, was in the 150th anniversary of Copernicus Symposium, because Copernicus changed the place of human being instead of Earth-centered to heliocentric. But he say, well, we are back to human-centered almost, because everything seems to be made from human beings to exist. Of course, we know physically we are not the center of the universe, but in terms of human our view of the universe seems to be created for us, for our living, for our benefit. I mean, non-Christians, atheists came to that conclusion just by looking at physical laws. And these are not the run-of-the-mill scientists. These are all people who have studied all the physical laws. Freeman Dyson, Dickey, all the people who created, who come up with the anthropic principle. All think about that way.
Well, Cynthia, you have really held forth, and you've been very, very helpful to us. I think we need to let you go, however, because it's getting late and you must be very tired. But thank you very much. It was a really excellent talk, and I think if we wanted to keep asking questions, we could probably keep you going all night. But I don't think we should do that. So I'm going to close this.
Have a different topic.
I'm going to close this meeting with a word of prayer, if you don't mind, and then we'll say good night. Lord God, thank you so much for the opportunity that we've had to learn about how you put this all together, and it just really amazing, Lord, that just our heads are spinning with all of the amazing coincidences, if you will, or I don't think they were coincidences. I think that you knew what you were doing, and but you were able to put it all together in a way that makes sense. And here we are, and there's no other explanation that is even partially acceptable. Is that you did it, Lord? Thank you, and you are marvelous and a wonderful creator. We just praise you and thank you, and we ask that you would now go before us as we go on to the other tasks that we have before us, and we ask for your blessing on each one of us. In Jesus' name we pray. Amen.